Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is Azaenolate. You can see the structure here. So we shall discuss mainly preparation of this material and its chemical reaction. But before going to details, one MCQ. So the question is, what is the major product of this reaction? For options are provided. I request you student, please pause the video, try by yourself, and whatever answer you get, please write in the comment box with a brief explanation. And don't worry, at the end of this discussion, we'll get the right answer. Now let's go back to the main topic, the introduction of this Azaenolate. It is also known as imines or imines. So actually, they are the nitrogen analogues of enolates. Okay. In fact, the imine gets treated with strong bases like LDA, deprotonation occurs, and highly nucleophilic azaenolates are generated. So basically, we'll learn these things slowly. Now, first of all, azaenolate preparation. So in order to prepare azaenolate, first this imine is prepared from the parent aldehyde and amine, and this imine has a tautomerism with enamine. By the way, I have already discussed about tautomerism in a dedicated lecture. You may visit for better understanding. Further, this imine and this enamine, when treated with LDA, then deprotonation of, whether you can consider this alpha proton or this NH proton, with strong bulky base, and ultimately it produces this azaenolate. So this is actually a resonance stabilized because it can come here and it can open, and in this way you can consider that this is resonance stabilized. So few questions associated with this topic. Let's learn stepwise. Question: what is sheaf base? Sheaf base actually nothing but a imine, means where this is not exactly hydrogen. So how sheaf base could be produced? They are produced by the reaction of carbonyl and amine, and the tricks for sheaf base preparation is, student, just take this oxygen and these two hydrogen from amine and remove them as water, and just attach this nitrogen with this carbon with a double bond. So this is the sheaf base or imine. Now generally we have observed that we always use LDA. Why? Actually, if you look at this LDA molecule, this has two isopropyl groups and N-. Now, the main reason to select LDA for many reactions for proton abstraction is really two reasons. First of all, it is a strong base, and second, it is a bulky base. Okay, so if it's a bulky base, means it selectively removes the proton or H+, or it cannot perform the nucleophilic addition. Why? As I told sometime before that it has two big isopropyl group. So because of steric reason or steric protection, these nitrogen can't act as a nucleophile. Rather than it abstracts the proton, because this proton is a very small atom and ultimately produces this anion, and these anions are resonance stabilized as I explained here. Now question: why these proton is abstracted, means H1, why not the H2? Because just consider, if the H2 is abstracted by LDA, what will be the conjugate base? Because acidity of any material is determined by the stability of the corresponding conjugate base. Okay, so the conjugate base is expected to look like this. This is the lone pair, or you can consider negative charge, and this is in the sp2 hybridized orbital. So there is no resonance stabilization of this negative charge. That's why, although this H2 is directly attached to these nitrogen, which is actually attached to this carbon, means in spite of being directly attached to the carbonyl group or imine group, this hydrogen has relatively lesser acidity compared to these alpha hydrogen, because the corresponding carbanion is resonance stabilized. Now third question: what happened if we use lithium amide instead of LDA? If you look at the difference between lithium amide and lithium diisopropyl amide, is these two isopropyl groups are replaced with hydrogen. This is the simple thing. So rather than, it's also an ionic compound, means this is N- lithium plus. Now this is not that much bulky, this lithium amide. That's why what it can do, it can act as a base. Not only that, additionally it can act as a nucleophile. So nucleophilic addition is also possible. So that's why this is not used, because we want a basic property. We want the basic property, not the nucleophilic property here. So that's why lithium diisopropyl amide is used, but not lithium amide. Now, secondly, the major benefit of using azaenolates is that they don't undergo self-condensation like aldol reactions from aldehyde. What do I mean by the statement? For example, if you take an aldehyde and treat with a strong base, okay, so treat with a strong base, for example, this base if you given, and it similar this base, it will produce this carbanion, and this carbanion enolate can all attack this aldehyde carbon again, and ultimately in this way it can produce this, that beta hydroxy carbonyl derivative. Means its workup is not done here, possible, but in case of imine this reaction is not possible. Means you do not have a risk that okay, this can attack here and it can open, so not possible. So that is the advantage, because this happened because the aldehyde, this carbon is not that much electron deficient, okay, and but they have some another interesting property, I shall come, and in fact they favor alkylation on the alpha carbon, because here the negative charge density is there. So that's why it can act as a nucleophile, and nucleophile it can react, it can favor alkylation. For example, if you treat with RX, I shall come everything step by step in upcoming slides. Now, a question is who is more nucleophilic between azaenolate or enolate from aldehyde or its derivative? So first of all, see, if you look at everything, there is the main difference is the replacement of this oxygen with nitrogen. Means these aldehyde are converted into imine, and from that imine is carbanion is produced or azaenolate is produced. We know that nitrogen is relatively lesser electronegative compared to oxygen. So electronegativity of nitrogen you can consider is less than electronegativity of oxygen. Okay, so that's why you can consider that the negative charge produced here is more stabilized because of the withdrawing effect of more electronegative atom. So you can consider this carbanion is relatively more stable. So if it is more stable, we can say it's less reactive. So that's why it is less reactive. So you may consider this carbanion is relatively more reactive, because charge density on this carbonyl alpha carbon is negative charge density on this alpha carbon is more, so it can act as a better nucleophile. Similar thing is observed if you compare this imine versus carbonyl, because this imine carbon is relatively less electrophilic compared to the carbon is aldehyde carbon. Okay, so that is the interesting thing associated with this enolate. Now let's discuss few application. For example, nucleophilic substitution reaction. This is a simple means azaenolate generation. I am not going. Azaenolate act as a nucleophile from its this carbon center, because carbon is softer in nature compared to nitrogen, because nitrogen is more electronegative, so it is hard. So first electron density will be pushed, and these carbon will attack at this carbon via a SN2 type reaction, and you may consider this is ring opening of epoxide under alkaline type condition, and this favors the attack on less bulky side. So this is student less bulky. Okay, by the way, I have already discussed a dedicated lecture on epoxide opening in presence of acid, base or Lewis acid. For better understanding about this concept, you may visit that video. So this reaction attack will happen on this less crowded site, because this nucleophilic attack is easier. Then ring opening of the epoxide will happen, which is actually a 3-member ring, strain ring. So after ring opening, it will produce this alkoxide derivative, and subsequently it will undergo hydrolysis using weaker acid like acetic acid. So means after hydrolysis, what it will produce? The oxygen, means hydrolysis means water addition. Oxygen will attach to this carbonyl group, and the water means 2 hydrogen What is the formula of water? OH2 or H2O. So these two hydrogen will be attached to this nitrogen, and in this way we shall get the parent carbonyl. See, from where this imine is generated, I have explained sometime before, through sheaf-based condensation with corresponding carbonyl, and in this case it is actually cyclohexanone derivative. So from here we are getting here, but ultimately what we are getting? We are getting this substitution on the alpha carbon of this carbonyl. Okay, so this is the overall discussion. Now let's discuss the another magnesium azaenolate and its application for SN2 reaction. Previous one also SN2 type reaction. This is a different type of reaction. First, this azaenolate is prepared. Preparation means first this carbonyl reacted with amine to produce imine. Then this imine undergo reaction with our MgX or ethyl magnesium bromide. We know Grignard reagent can do two reaction. One is base and second it can act as nucleophile. So in the first step it is acting as base. Base means this ethyl minus is abstracting this proton and ultimately it is generating the carbanion derivative of this. Okay, so this is the minus. Now it has a canonical form, means it can come and it can open. So consequently we can say that this nitrogen center will have relatively more electron density. Why? Because nitrogen is more electronegative, so it will prefer to keep or hold the electron density on itself. But holding electron density on anywhere is associated, with some destabilization, and magnesium plays the role because these excess electron density is donated to magnesium 2+, which is actually Lewis acidic in nature, means it stabilizes the electron excess on this organic molecule. Now second thing, it will act as a nucleophile. Now I told that this nitrogen center is not that much good nucleophile. Why? Because it is harder in nature, whereas if you compare carbon, that is softer, so carbon can act as a better nucleophile. So consequently what happens? This from this carbon center it pushes, this reaction happens, so more specifically on this carbon, and ultimately this Br leaves, and this is via SN2 type reaction ultimately produces this. Now still it's imine derivative. So how hydrolysis is done? Water, H2O. So this oxygen goes here and this water goes to amine. So along with this, in this case what it will produce? RNH3+. Why I am saying 3+? Because HCl is used in this medium, so 3 plus Cl minus, and along with that alpha substituted or alpha carbon alkylated ketone derivative. Okay, now let's discuss another example, that is nucleophilic substitution on alpha haloketone protected. What do I mean protected? Look at this example 15. What, from where it produced? It produced the from corresponding the aldehyde, and this is Br. And how this protection? Through ethylene glycol. So this part came from, ethylene glycol 1,2-diol. So this is actually nothing but acetal formation. I have already discussed some lectures on this, you may visit for better understanding. Now so this is actually a carbon bromine bond. Okay, similar nucleophilic substitution possible, like as I discussed previously. So in this case, first this imine is taken, is treated with LDA. HMPT means hexamethyl this phosphoromide derivative. So ultimately what it produces? It produces, means first after deprotonation it produces the carbanion, that it is resonance stabilized. So here so I am not going, you have learned a lot during this discussion. So next phase it will attack here via a SN2 type reaction. So in this case it will leave, ultimately it will produce this. Now if you want to get the carbonyl derivative corresponding, so do the hydrolysis, means H3O plus. We know acetals are hydrolyzed in presence of this acid. So acetals, remember, they are stable in base but they are unstable in acid. So what will happen, that this part will be hydrolyzed, so it will produce this hydrogen, this R1 R2 derivative, along with that this is aldehyde. So you can see this is a derivative of 1,2,3 dicarbonyl derivative, and see the yields are significantly good. Now question, this is a strategy, means protection of aldehyde to get reaction, and later on the aldehyde is deprotected. So no, I guess I made a mistake. Mistake means this will not be the thing, this, because there is one, this is 1 2. No, not is, this is not 1,3 dicarbonyl, this is student 1,4 dicarbonyl. And by the way, 1,4 dicarbonyl compounds are very much important for 5-member heterocyclic compound preparation. So please visit, I have already discussed a dedicated lecture if you have any doubt. Now, so this is a strategy to selectively functionalize aldehyde in presence of ketone, because just forget, if you do this reaction, means this carbanion along with this aldehyde derivative, then what is expected? That is a competition, nucleophilic substitution of this bromine versus nucleophilic addition, means this can also attack here. So in order to get the selective nucleophilic substitution on alpha haloketone protected, such kind of strategy is utilized. Now another explanation, another example, aldol type reaction. So just the side reaction I was talking, this one. What happens? So after using magnesium bromide triethylamine acetonitrile. Now student, I need to give some brief about this triethylamine. This triethylamine is actually a specific proton scavenger, or it mainly acts as a base. Because this 3 bulky ethyl group, it is not a good nucleophile, but there are some exception cases. For example, if you react with acetyl chloride to do ester formation, in that case generally we use triethylamine. What it does, it do nucleophilic substitution, nucleophilic acyl substitution type, but it is not actually a good nucleophile. So you can consider this is act as base. So what it does, it abstract this proton. Now a question will come in your mind that, sir, previously you are talking about LDA, which is a big base, which is a strong base. The same work is doing by triethylamine, mild base like triethylamine. Is it possible? Actually this is possible because of a reason, presence of this magnesium bromide. See, this magnesium bromide is nothing but it's a Lewis acid. So what it does, it coordinates with this nitrogen lone pair magnesium 2+. So after this coordination, the electron deficiency of this nitrogen increases, means you can consider that a canonical form possible. So this is N, this is double bond, this hydrogen, just I am focusing on the actual part, and this is when it coordinated to magnesium, then some electron deficiency will arise on this nitrogen. Consequently, it will prefer to make this canonical form, means this double bond will open, and ultimately this nitrogen will have a positive charge, this. So what does it means actually? It means an activation of carbonyl group. Imine is also a carbonyl derivative. So activation of carbonyl group or increase of electron deficiency or electrophilicity on this carbon atom because of this Lewis acid. Okay, so this is the role. Means because of that, this triethylamine is capable to abstract this proton, and it can produce the corresponding carbanion. Means you can just forget this. So this is a carbanion here. Okay, and this carbanion is also resonance stabilized because of this coordination with magnesium. Now next step, it attacks here, and ultimately it produces this aldol because it's an beta hydroxy carbonyl compound. Okay, so in this way it produces aldol type product, but surprisingly the yield, look at student, it's 20%. It's pretty less, or you may consider it's a low yield reaction. Question why? Because this carbonyl is not that much electron deficient or activated, student, and that's why in case of Mukayama aldol addition, you see the titanium tetrachloride is used. Okay, so that's, please remember that why generally we use a Lewis acid when we do any this enolate derivative and you react with carbonyl group. So this is another explanation. I know it's a negative example, but this negative example gives us some idea or reason behind the selection of Lewis acid like titanium 4 is a very strong Lewis acid in this Mukayama aldol reaction. Now let's come to very interesting another example, that is asymmetric alkylation by azalactone. Question, why asymmetric? Because in this case an asymmetric center is there. Okay, so you may consider this is actually asymmetric imine, and from how it is produced, it is produced from this corresponding cyclohexanone. So this is the carbonyl. Along with that, this is, you may consider this is the pH, and so hydrogen is obviously, sorry. So this is the amine and another is hydrogen. So you can consider that this center is asymmetric. So when sheep base condensation is done, so it produces this asymmetric imine. This is asymmetric imine, and these asymmetric imine first undergo deprotonation using LDA THF. Now student, what about this THF? This THF is obviously anhydrous THF or dry THF. Why? Because if there is moisture in the reaction medium or solvent, then the base or this lithium diisopropylamide will be quenched, and corresponding what it will produce? It will produce lithium hydroxide and this diisopropyl amine, means this NH. So it is a waste of base. So that's why anhydrous solvent needed. Not only anhydrous solvent, the air above this reaction should be replaced with nitrogen, or you may consider better is anhydrous nitrogen, like Schlenkline type. Fine. So in this way, this LDA will first deprotonate this and ultimately deprotonate this one, and ultimately it produces this anion. It will react with Rx. Okay. Now in this case, you can see the enantiomeric excess is 82% and overall yield 88 to 95%. Question, why? See, because the chirality is previously introduced here in the compound, that's why enantioselectivity is there. So you can consider that this reactant is chiral. So if the reactant is chiral, then it will also favor. So what is the intermediate in this case? It will produce intermediate in this case, it will produce this. So this is the R, this is nitrogen. Now here this is OMe1 and this is down pH. Okay, so that is the main reason why we get this enantioselectivity. And in the second step, you can see after hydrolysis, this imine bond is broken and it produces the final selective ketone. And by the way, student, remember, asymmetry at the alpha carbon of carbonyl is really difficult. Why? Because the main problem is enolization, or you may consider Keto-enol tautomerism. So that's why this is very important, and such kind of problem is observed in many time in case of peptides, because peptides are, you may consider this is the NH2 and this is alpha carbon, so substitution there. So in this case there is hydrogen, and if it racemizes, peptide racemization means everything could be changed, and that's too much dangerous. By the way, I've already discussed a dedicated lecture, this peptide racemization versus tautomerism. You may visit to learn this unique concept. Okay, now let's come back to our discussion. So what we have learned today, in conclusion, we have learned that sheep base can easily formed by carbonyl, means aldehyde, and imine. Aldehyde is better because less bulky, so it's favored because of the Burgi-Dunich trajectory or Bargi-Dunich trajectory concept. Now Azaenolates are better nucleophile than corresponding carbonyl derivative because the negative charge density on the alpha carbon is more here. Now here, low chances of self-condensation type reaction. It is a better nucleophile than protected enolate due to enhanced charge density on the alpha carbon. And finally, what we have learned, that this asymmetric synthesis could be achieved using chiral amine. Okay, so that is another thing, because sheep base condensation is a very easy reaction. So that easy reaction, you can produce a chiral molecule. From there you can produce enantioselective particular product or particular stereoisomer in enantiomeric excess. Okay, so now let's come back to our question. So what is the major product of this reaction? Student, please look at this example little carefully. What reagent I have given? Lithium aluminium hydride. So this is actually a very selective reagent for carbonyl or carbonyl's derivative reduction, and this is actually a very reactive reagent. We know that lithium aluminium hydride reduces carbonyl or imine to corresponding amine, so it will attack here and it will open up. So in the first step, what it will do, it will first reduce this imine into corresponding amine derivative. Fine, means in this case it's an hydrazone, it's a substituted hydrazine. One side substitution is this, another side substitution is this. Finally, then workup. So after workup we will get this compound, and second step is the use of ranitol. Ranitol is actually a porous nickel containing nickel hydrogen material which is useful for reduction, and actually what it does, it reduces these bond to this nitrogen bond, because we know these such kind of bonds are not that much stable. Why? Because the lone pair repulsion is actually a very detriment. It's not a good thing. Because of this lone pair repulsion or alpha effect, such molecules became very much reactive. So in presence of ranitol, they undergo reduction and ultimately produces this amine. So this is the overall reaction, and by the way, I have already discussed a dedicated lecture on this ranitol too. You may visit for understanding about this chemical better way. So what is the answer of today's question? MCQ is option D. Okay, now if this question is given to you in your exam less than 30 seconds, how can you solve? First of all, lithium aluminum hydride selectively reduces the carbonyl derivative into the corresponding saturated one, so imine to amine. Final, just so this point, and in this case there is another reagent, nickel hydrogen, ranitol. This is a extremely reducing agent, so maximum what reduction possible after that. So what is the weakest bond here? In this case the weakest bond is, student, this nitrogen bond. So this is the weakest, so it will break and corresponding amines, option D. Now why not other? See, this is the intermediate, so not possible. So if you look at this carbon bond broken, student, it is not that much easy, it's gone. Second, third one, this carbon nitrogen, it is also stronger possible. So what it will break? This nitrogen and ultimate is this. So first of all knowledge, second practice, third common sense. You can end up this answer very soon. So this is the end of this discussion. I believe this video may be useful. If it is, please help this channel to grow, and if possible please visit my another channel, Climate and Chemistry, where I upload global warming and climate change related videos. Thanks for watching. See you in my next video. Bye bye.